In September of 2023, an archive scientist at the European Space Agency was doing something almost mundane, scrolling through a batch of deliberately unfocused test images sent back by a brand new space telescope during its earliest calibration checks, images that were never even meant to be scientifically useful. And in one single blurry frame, he spotted something that made him stop scrolling entirely. A faint glowing circle of light, wrapped almost perfectly around the center of a galaxy that astronomers had already been studying and cataloging for more than 100 years. That circle turned out to be one of the rarest, most visually striking phenomena predicted by Albert Einstein's own theory of general relativity, hiding in plain sight around an ordinary, thoroughly studied galaxy, completely undetected until this exact moment. And that discovery was only the opening act. In the years since, the same broad scientific effort this telescope was built to lead has turned up something considerably stranger, an invisible object with the mass of 1 million suns, sitting billions of light years away, whose basic internal structure does not match anything scientists currently know how to explain. This is the real story of what the Euclid Space Telescope has actually found, and why some of it remains, right now, genuinely unexplained. To understand why any of this matters, you first need to understand what Euclid was actually built to do, and why the scientists behind it call it the Dark Universe Detective. Euclid is a space telescope operated by the European Space Agency, with contributions from NASA, that launched from Cape Canaveral on July 1st, 2023, beginning a planned 6-year mission with one central, enormously ambitious goal, mapping more than a third of the entire sky in extraordinary detail, observing billions of galaxies stretching back across 10 billion years of cosmic history. Its entire purpose is to help scientists finally make progress on two of the biggest unsolved mysteries in all of modern physics, dark matter and dark energy, the invisible substance and the mysterious force that together are believed to make up roughly 95% of everything that exists in the universe, while remaining almost completely undetectable through direct observation. Euclid's specific strategy for tackling this problem relies heavily on a phenomenon called gravitational lensing, a direct consequence of Einstein's general theory of relativity, in which the mass of a foreground galaxy or cluster of galaxies actually bends and distorts the path of light traveling toward us from something sitting much farther away, behind it. By carefully measuring exactly how that light gets bent and distorted, scientists can effectively map out the mass, including invisible dark matter, concentrate it in the foreground object doing the bending without ever needing to see that mass directly at all. The specific event that first caught global attention happened before Euclid's real scientific mission had even formally begun. Before any spacecraft can start its actual survey work, engineers and scientists have to run through a careful commissioning phase, testing every instrument to make sure everything functions correctly. And during this early testing period in September of 2023, Euclid sent back a batch of images that were deliberately left out of focus, since the goal at that stage was simply confirming the instruments worked, not gathering usable scientific data. Euclid archive scientist Bruno Altieri, whose job involves routinely reviewing this incoming data as it arrives, described his own process in strikingly simple terms, explaining that he looks at the data from Euclid as it comes in, and that in one specific blurry frame, he noticed a hint of something unusual enough to warrant a much closer look. What he had spotted turned out to be a nearly perfect Einstein ring, an extremely rare and specific form of gravitational lensing that occurs only when a foreground galaxy happens to be almost exactly aligned with a background galaxy from our particular vantage point on Earth, bending that distant galaxy's light into a complete glowing circle surrounding the foreground galaxy's center. The galaxy responsible, called NGC 6505, sits a comparatively modest 590 million light-years from Earth, and astronomers had already known about and studied this particular galaxy since the 1880s, without ever detecting any sign of this specific phenomenon happening around it. Thomas Collett, a professor at the University of Portsmouth's Institute of Cosmology and Gravitation, who worked on the follow-up research, explained exactly why this specific discovery generated so much genuine excitement within the field, noting that this particular gravitational lens is special precisely because it sits in our own cosmic backyard. Close enough, in fact, that astronomers had already been observing this exact galaxy for well over a century. And yet, it took Euclid's specific resolving power to finally reveal that it was secretly functioning as a gravitational lens the entire time. Connor O'Riordan of the Max Planck Institute for Astrophysics, who led the first formal scientific paper analyzing this specific Einstein ring, explained the broader statistical context that makes finding one this clear and this nearby so remarkable, noting that fewer than 1,000-strong gravitational lenses of any kind were known prior to this discovery, and that finding one this spectacular, this early in the mission, and this close to Earth, genuinely surprised the entire research team. That discovery alone would have made for a remarkable start to Euclid's mission, but it also represented only a small preview of the telescope's actual intended scale. Mission scientists have stated that Euclid is expected to ultimately discover somewhere around 100,000 strong gravitational lenses over the full course of its planned survey, a staggering increase over the fewer than 1,000 previously known before the mission even began, each one offering a new opportunity to map otherwise invisible mass scattered throughout the universe. In March of 2025, Euclid released its first major public data trove, including a preliminary catalog of roughly 500 additional gravitational lens candidates, compiled using a combination of artificial intelligence, assisted searching, and direct contributions from citizen science volunteers, alongside a first classification survey covering more than 380,000 galaxies. An early demonstration of the sheer analytical scale this mission is specifically designed to eventually achieve. The same broad scientific effort, using gravitational lensing to hunt for otherwise completely invisible objects scattered throughout the universe, is precisely the context behind the second, considerably stranger part of this story, one that remains genuinely unresolved as of right now. In October of 2025, a separate international research team, led by Devin Powell at the Max Planck Institute for Astrophysics, announced the discovery of an object with a mass roughly 1 million times that of our own Sun, detected not through Euclid's own imaging directly, but through an entirely complementary technique, an enormous coordinated network of radio telescopes scattered across the globe, including the Green Bank Telescope, the Very Long Baseline Array, and the European Very Long Baseline Interferometry Network, all linked together and precisely correlated to function as a single Earth-sized virtual telescope. This combined network detected the extraordinarily subtle gravitational distortion this invisible object imprinted onto the image of a distant, thin lensed radio jet, allowing researchers to measure its mass with a statistical confidence described in the resulting paper as extremely robust, a result so precise that its uncertainty margin came in at just over 3%, an extraordinary level of confidence for an object that cannot be directly seen or photographed in any conventional sense at all. Powell described the fundamental challenge and strategy behind this entire technique plainly, explaining that hunting for dark objects that do not appear to emit any light of their own is clearly difficult, and that researchers instead rely on very distant background galaxies, functioning as a kind of natural backlight, allowing scientists to search for the gravitational imprint these invisible objects leave behind, rather than any light they might otherwise produce. At the time of its initial announcement, this discovery was already notable simply for its precision and its unusually low mass compared to typical dark matter structures detectable through this kind of lensing technique, representing the lowest mass object of its kind ever measured at such an enormous cosmological distance. But the genuinely strange part of this story did not fully emerge until a follow-up analysis published in the journal Nature Astronomy in January of 2026, when the same research team, led this time by Simona Veghetti at the Max Planck Institute, conducted a considerably more detailed examination specifically targeting the object's internal structure, attempting to determine exactly what kind of object this actually was, rather than simply confirming its total mass. Veghetti described the process candidly, explaining that trying to separate all of the different mass components of such a distant, low-mass object using gravitational lensing proved both extraordinarily challenging and genuinely exciting, adding that just when her team believed they had finally pinned down its properties, the object's characteristics threw them yet another curveball entirely. Here is what that deeper analysis actually revealed, and why the scientific community is now treating this specific finding with such evident ongoing puzzlement. According to the standard widely accepted model of cold, dark matter, an invisible object of roughly this mass, detected at this specific cosmological distance, should behave in one of two predictable, well-understood ways. It should either resemble a simple, extremely compact object, something like an isolated, free-floating black hole with no surrounding structure at all, or, alternatively, it should resemble a diffuse, roughly spherical halo of dark matter, the kind of loosely distributed invisible mass concentration standard cosmological models predict should be scattered abundantly throughout the universe at exactly this general scale. When Veghetti's team tested the actual data against both of these established possibilities, neither one fit. The object's structure instead pointed towards something researchers had not specifically anticipated finding, an extremely compact core, potentially a black hole or an unusually dense stellar nucleus, embedded within a surrounding extended disk of additional mass that, remarkably, also does not appear to emit any detectable light of its own. The resulting published paper describes this specific combination of properties as a possible genuine challenge to both the standard cold dark matter model and its alternative. Warm dark matter, two of the leading theoretical frameworks currently used to explain how invisible matter is actually structured and distributed throughout the universe. It is worth being precise and honest about exactly what this specific finding does and does not actually demonstrate, since that precision is exactly what separates a genuine, significant anomaly from manufactured, overstated mystery. Nobody studying this object is claiming to have detected anything resembling exotic new physics or any violation of general relativity itself, the fundamental theory that predicts gravitational lensing in the first place, that has, in fact, just been used with extraordinary success to detect this very object. What researchers have genuinely found is an object whose specific internal mass distribution does not cleanly match either of the two standard categories cosmologists generally expect an invisible mass concentration of this size to fall into, raising a genuinely open question about what other kinds of structures might exist in this particular, poorly understood range of cosmic mass scales, structures current theoretical models simply were not built to anticipate or account for. This kind of finding matters enormously for the broader project Euclid itself was specifically designed to support, because objects exactly like this one, small, invisible, and difficult to characterize precisely, represent exactly the kind of substructure scientists need to study in far greater numbers if they hope to meaningfully test and refine competing theories about the fundamental nature of dark matter. A single, unusual object, however statistically robust its detection, cannot on its own overturn an entire established cosmological framework. But finding even one clear example of an invisible mass concentration that does not fit into any previously expected category is precisely the kind of genuine anomaly that motivates researchers to systematically search for many more examples like it, using exactly the kind of large-scale, high-precision gravitational lensing survey that Euclid itself is specifically built to conduct across its full 6-year mission. Step back and consider what these two distinct discoveries, taken together, actually reveal about where this entire field of research genuinely stands right now. Euclid's own serendipitous discovery of a stunning, previously invisible Einstein ring around a galaxy astronomers had already studied for more than a century demonstrates just how much genuinely new information remains hidden in plain sight, waiting only for sufficiently precise instruments to finally reveal it. And the considerably stranger, still unresolved puzzle of a million solar mass object whose internal structure does not match any standard theoretical prediction demonstrates that even our most fundamental, widely accepted models of how invisible matter is actually organized throughout the universe may still be missing something important, some category of structure nobody has fully anticipated or explained yet. Neither of these findings represents broken physics. Both of them represent something arguably more valuable, genuine evidence that our current maps of the universe's invisible architecture remain incomplete, and that the tools now coming online, Euclid chief among them, are finally sensitive enough to start revealing exactly where those gaps actually are. So here is the honest, complete picture of what Euclid has genuinely captured, and why some of it remains authentically unexplained. A test image nobody expected to be scientifically useful revealed one of the rarest phenomena predicted by general relativity, hiding around a galaxy studied for more than a century without anyone noticing. And the broader scientific effort surrounding this same technique has already turned up an invisible object whose basic structure does not fit comfortably into either of the two categories standard cosmological theory currently offers. A genuine, still open puzzle actively being studied by some of the same researchers directly connected to Euclid's own ongoing mission. Euclid is not finished. It has years remaining in its planned survey, and mission scientists have been explicit that it is expected to eventually catalog around 100,000 gravitational lenses in total, each one a fresh opportunity to map more of the universe's invisible structure, and potentially to find more objects that, like this one, simply refuse to fit the categories scientists currently have ready for them. If you want to see what Euclid uncovers next as it continues its survey of the sky in the years ahead, subscribe and turn on notifications. Because this telescope has already proven it can find genuine mysteries hiding in places nobody thought to look, and it has only just gotten started.